everybody, and welcome to the Cosmos Show, place to be if you're curious about the universe. I'm your host, Dr. Sam from Wyoming Stargazing. Here you can get advice from an astronomer, pick the brain of astrophysicists, and find out what astronomers have to say about life, and find out about all the cool stuff happening above your head, all in the same place. So thanks for joining us. This week's show is all about exosolar planets, planets that orbit around other stars. So we'll discuss how astronomers are finding those exosolar planets using TESS, the Transiting Exoplanet Survey Satellite. And our special guest tonight is Natalia Guerrero, who is a consultant for TESS, and so she'll tell you all about that when we get down to the guest spot. But before we get there, let's welcome our co-stars. First, PhD candidate in astrophysics from the University of Chicago and host of her own YouTube show, Nora's Guide to the Galaxy. It's Nora Bailey.
Hi, everyone. Glad to be here.
Glad to have you, Nora. Next, postdoctoral scholar from the Simons Observatory. It's Dr. Nick Gilsky.
Hey.
Hey, Nick. And last but certainly not least, medical doctor and founder of Orbital Biodesign, it's Dr. Danny Carroll.
Hi, everybody.
Hey, Danny. And unfortunately, Dr. Lauren Corleys isn't able to join us tonight. We're not going to have her next time either, but she'll be back with us in October. Tonight, it's Nora's turn to tell us all about what she's up to with her research. So Nora, we are all yours.
Awesome. So my first update is that today is actually my birthday. So I'm really happy to be here with you guys. Just had a lovely sushi dinner with my boyfriend. But anyway, so what have I been up to? So today I'm going to tell you guys about a project that I'm just finishing up that I've been working on for about a year or so. And it's called Period Ratio Sculpting Near Second Order Mean Motion Resonances. And don't worry, we will talk a little bit more about that. But first, I want to add a little bit about academic publishing because you might not know that much about it. I certainly did not. Next slide, please. So this is kind of a very brief flowchart that I made of what happens when you are trying to basically produce scientific work. So this big block up at the top is what is the work. It's the science, it's doing the research, it's what we all want to be doing. And it's going to look really different for everyone. So for me, doing a research project is usually working on my own with some advice from my advisor, but pretty much by myself, usually doing math and simulations on my laptop or maybe on a computing cluster. It looks really different for science, like everywhere. There could be big collaborations, you could be observing, you could be building an instrument, like very different. But this next part is pretty much, as far as I know, the same for everybody. And it's not always the most fun. So as you're doing your project, you're probably gonna be writing a draft kind of in parallel, but eventually once the project is done, you're gonna look at your results and you're gonna say, is this worth publishing? Hopefully it is, because you probably just spent a long time on that project. And if it is, then you're gonna finish writing your paper draft. And then you're gonna be like, okay, is this draft good enough? Can I submit this somewhere? There might be working with collaborators here at this point, like getting advice, getting feedback, trying to produce a draft that's submittable. So then you have to decide where to submit. There's a lot of different journals out there and they all have kind of different reasons you might want to publish there. For example, Nature is kind of going to be like a big splashy journal. I've actually published all of my work in the AAS journals, which is going to be the Astrophysical Journal and the Astronomical Journal. Actually, all my papers are in the Astronomical Journal, which, fun fact, is usually where observers publish their results. And Astrophysical Journal is usually more for theorists. And I'm a theorist, so this is kind of strange. Fun fact, celestial mechanics is like grandfathered into AJ instead of FJ, which I did not know until the first time I went to publish a paper. And I was like, wait, why am I submitting to AJ? So then once you submit the paper, it will go to an anonymous referee. So the number of referees that it goes to kind of depends on the paper. The AAS journals just use a single referee. And this is anonymous, and they are going to review the paper and then send a referee's report. Now, the kind of thing we all hope to happen is that they're going to be like, great paper, good job, accept it. But usually there's going to be some sort of revisions requested. And this whole cycle down here in the bottom is called peer review. And peer review is not always a lot of fun, but it's really important because this is kind of where hopefully someone might catch bad science or, A lot of times you've been working really closely with this project for a year, and like you might not even see the areas where, one, you're not being clear in your paper, or two, you've just kind of like skipped over things that really needed to be done. So it's a really important part of the process, but it's not always the most fun to be in. And that is the part that I'm in right now for this project. So I just got my referee report back about 2 weeks ago, and unfortunately they did not recommend it for publication unless I addressed some major comments that they had. So I am currently working on that and hopefully getting it up to snuff. And while, again, this wasn't the most fun report to get, it's really like making the paper so much better. I can definitely tell that it's much better. So very thankful to this anonymous referee, because also keep in mind, these referees do this for free. They're not getting paid for this. This is just a part of being a scientist, is you read other people's drafts for fun. And then they might reject it if it's just, there's no way that it's going to become up to snuff. So that's kind of the whole process. And it doesn't end here. Once it gets accepted, that's like, yay, but then you still have to go through formatting and you have to pay. So scientists pay to get their work published in journals. And it's actually pretty expensive. So my last paper, not this one, but my last paper cost over $1,200 just to get published. So again, I'm not like opening up my wallet and like shelling that out. It came out of my advisor's grant, but it's a pretty hefty fee, and it can definitely be an issue with how much money these are getting. Also, fun note, the AAS journals are actually going to open access next year. So no more paywalls for AAS journals, which is really exciting. Although if you are running into paywalls and you're like, oh, I really want to read this paper, FYI, there's a site called archive.org where scientists in physics and astrophysics and other fields as well, I assume, but definitely physics and astrophysics post what are called preprints, which are basically just draft versions of their papers. So you can usually get those for free if you want to. Okay, so that's publishing in a nutshell. And that's been kind of consuming a lot of my work. But let's talk a little bit about the actual work. And I won't go too much into this because like most projects, it's very narrow and very niche in its scope. Next slide, please. So I just want to break down this title for you, because even the title is kind of dense if you're not in this subfield. So first off, what the heck is a period ratio? So if you have multiple planets, 2 planets, you can compare their periods by dividing them in a ratio. So for example, Jupiter and Earth have a period ratio of about 11.8 because Jupiter's period is about 11.8 times that of Earth. And periods are something we can measure pretty easily for like transiting exoplanets. So for example, this figure that I'm showing here is a well-known result for multi-planet systems from Kepler. So Kepler was a mission that observed thousands of exoplanets and measured a lot of periods. And so you can make this kind of distribution of what periods happen. Now, the mean motion resonance part is just if that period ratio happens to be an M to N ratio where both of those numbers are integers. Now, keep in mind when I say period here, so there's multiple periods involved in a planet, right? It could be the spin period, like Earth's spin period is 24 hours. But in this case, we're talking orbital periods. So that's going to be the time it takes to go around the star. So for the Earth, that'd be 1 year. And if these like numbers are integers, then you get some kind of really cool dynamics. It's basically just like a really exciting thing that happens. So some of these have been pointed out on this figure here. You can see like the 2 to 1, the 3 to 1. So those are some mean motion resonances. Now, the order of a mean motion resonance is just the difference between M and N. So a second order mean motion resonance just means that M is 2 times or plus 2 bigger than N. So for example, the 3 to 1 would be a second order resonance. Now, the lower the order of the resonance, kind of the bigger the effects are going to be. So first order resonances are really kind of take up most of the attention and get really like, people get excited about first order resonances. But in this paper, I was interested in second order resonances because they actually have a slightly different shape. I'm not going to get into what I mean when I say that, but they have a slightly different shape than first order resonances. And I wanted to explore one of the implications of that. So next slide, please. This is kind of the big takeaway, I think, of my paper. Now, keep in mind, this is one figure. The paper has 24 figures in its current form, so I'm really just showing you a taste here. But basically, because of the shape of the resonance, over time, the period ratio of the planets changes. So it's not going to be 100% constant all the time. So if you have a planet pair that's in resonance, so let's say it's in the 3 to 1 resonance, it might have at one point in time a period ratio of 3.01 and another point in time a period ratio of 2.99. And because the second order resonance is symmetric around the resonance, it actually averages out to the exact resonance location if you average the period ratios over time. And so this is actually what I'm showing in this figure. So this is about several hundred planet pairs that I simulated. And I basically took the period ratio at a single random point in time, and that's shown in green. And then I averaged it over a period of time, and that's shown in purple. And you can see that with the averaged period ratios, all of a sudden you get this really, really narrow, really, really tall spike right at the resonance location. And that's really exciting. That was kind of what I was hoping to see, and I did. And this sort of behavior is much more apparent for more eccentric planets. So that is planets that are on less circular orbits. And so kind of looking for this peak can be a signal of eccentricity in a population of planets. And so one of the things we did in this paper was actually look for this signal in some Kepler populations, and we didn't really find it, indicating that Kepler planets probably have pretty low eccentricities, which is something that people have proposed using other methods. So this is kind of confirmation of that. But yeah, so that's the project that I've been working on for the past year or so that will hopefully be published sometime soon once I get this referee report all taken care of.
Does our solar system have any resonances?
Yeah, actually, there are resonances all over in the solar system, not between any of the major planets, although Jupiter and Saturn are really close to, I believe, a 5-2, and probably that resonance did play a role in the history of the solar system, as the planets have moved around probably. But this is especially, we see a lot of resonances with small bodies in the solar system. So for example, Pluto is in a mean motion resonance with Neptune. This is one of the reasons that Pluto is it's actually on an orbit that crosses Neptune's orbit, but because they're in resonance, Pluto is actually protected and hasn't gotten scattered out. Jupiter, kind of the big dog in the park, right, has a bunch of resonances with the asteroids and kind of cleans out these empty gaps in the asteroid belt, because really close to resonance, it causes a lot of instability, whereas being actually in the resonance can sometimes provide protection from instability. So yeah, we see lots of resonances in the solar system.
How do the actual moons of a given planet affect some of these dynamics? I'm kind of curious, like the moons of Jupiter, how does that play, or how do those play in?
Yeah. So generally the effect of the moons on the planets themselves isn't going to be a strong enough effect to be seen in something like this. But moons themselves can be in resonance. Actually, you mentioned the moons of Jupiter. They are actually in resonance, and not only in a 2-planet resonance like we're considering here, but actually a resonant chain where you can have multiple planets that are like all in resonance with each other. And so, yeah, we get that with moons as well.
Nori, I think you mentioned briefly like how astronomers could actually look for this resonance pattern in old data sets. What do you envision astronomers using this for, like moving forward? What is it going to help astronomers do?
Yeah, so I mean, astronomers have been interested in resonances for a long time. This particular signal, I think, will be helpful for constraining eccentricities. So that's kind of the main takeaway is how the eccentricity affects this. Just because the resonance is much wider, and so very eccentric planets can be kind of farther away from the exact resonance location and still be in resonance. But eccentricity is really hard to measure for transiting planets, and so I think that will be basically a hopefully important way to use this.
Very cool.
So hopefully that wasn't, I didn't get too far into the weeds for you guys.
Yeah, I mean, it's super cool stuff. I think, like, as you said at the very beginning, it's definitely a niche field without a doubt.
Yep. It's a niche field, and I feel like I work in a niche part of a niche field. But I enjoy it. It makes me happy.
That's awesome. Well, thanks so much for sharing. I really appreciate it.
Yeah.
So it's time for our next segment, which is Astro Advice, the new name for Nobel Notes. And the reason we decided to call it Astro Advice is that we noticed that our list of Nobel laureates whose quotations we were using was conspicuously occupied by old white guys. not too surprising, unfortunately. Until the list of Nobel laureates in the sciences are gender balanced, and even though Nobel Notes has a nice ring to it, we're going to be more inclusive, and we're going to use quotations from all astronomers, especially women astronomers. Tonight's focus is exosolar planets. And so our quotation tonight comes from Dr. Joanna Teskey, an exoplanet researcher at the Earth and Planets Laboratory at the Carnegie Institute for Science. And Dr. Teskey says that questions like, what is going on here? Why does this happen? How does that work? Are the types of questions that drive people in STEM fields, science, technology, engineering, and math. That's what makes those folks excited to get up in the morning and to get working, figuring things out. And that certainly resonates with me. Even though I'm, more of an educator than a researcher, it's definitely answering those questions and helping other people to understand the answers to those questions really, gets me going in terms of being enthusiastic about science education. So yeah, love to hear your thoughts on that.
I think that that what she's really getting at is this sense of curiosity, in why the world works in the way that it does, and that applies to, in my mind, that applies to any arena within science. So not necessarily just like the stuff that Nora was talking about, but even on the medical side, certainly in engineering, trying to figure out why things happen the way they happen, and not just why they happen, but what that means, what the implications are moving forward. I know on the medical end, oftentimes we look at, what's the end game, kind of how does it impact the patient, or how does, a given physiologic process or, biological insult that is sustained by the body, what's the net effect of that? And I think the parallel to that in a lot of other fields, is what, just like what's the end result? So why should we care, essentially, but in a very positive way. So.
Yeah, I think this is so applicable to exoplanets because it's such a young field. And so it's like every time we discover things, like it's like we didn't know that. Like the first exoplanet was a hot Jupiter, and we're like, we didn't know Jupiters could be that close to a star. Like it's just like totally crazy. So I think especially with like younger fields, this is definitely very true. And I think, humans are innately curious, and I feel like they're going to come up with an answer they're going to come up with explanations. And science, like the job of science and the job of science educators is to make that explanation reliable and not a conspiracy or not, bad junk science. And I see people a lot because I do science communication, and I see people that are very smart people, that are very curious people. And when they see these sorts of questions and they think, what's going on here? And they don't get the right answers, or they don't get like a scientific explanation, they choose a different explanation. And I think that's a shame. And so that's something that I hope that, educating, we can teach people that the answer to, something weird is going on here is not necessarily, it's a sign that there's a conspiracy. Maybe it just means we have more science to learn.
Yeah, I'm glad you brought that up, Nora. That's exactly where my mind first went when I saw this quotation, just like how important the work of science educators and communicators is right now in our society. Like the prime example is like the COVID conspiracies, but like that's not the first time we've had conspiracy theories, obviously, right? And being able to ask these questions from a scientific perspective and know when you're looking at answers that one answer actually comes from reputable scientists versus politicians is so important. So I think the more we can actually get people to, ask these questions to themselves, like not just scientists asking them, but everybody asking them these questions from a scientific perspective, the better off we're all going to be. Anybody else have anything? Oh yeah, Nick, go for it.
Yeah, no, I'm looking at this and wondering what the intonation was when she spoke this, because on the really, basic scientific wonder, exploring the universe, it's, what is going on there? Why does that happen? How does that work? Versus my more common usage in the lab of what is going on there? Why is that happening? How does that work? And I both are part of the scientific process, but they get a lot of use in different circumstances.
I have said that many times about my code.
Like that.
Especially code that I wrote like 6 months ago, and then I'm coming back to it. What is going on there?
I can
what I told you
personally
to do.
my experience was the very first scientific presentation that I ever gave was on a hypothesis that ended up being dead wrong. And so we had to basically, we were presenting to this crowd of global health, specialists and saying, oh yeah, so we thought there was definitely going to be a difference, like a significant difference. And we were completely wrong. There wasn't one, which was still scientifically valid, and very important and useful, but it can be kind of a kick in the face, or it can feel like that sometimes, Yeah,
so. I mean, and that is sometimes I think the most exciting part about science. We can go down one path and then find out something totally different than what we were expecting, which is pretty cool stuff.
Yeah, and I think too, one thing that I really like, I think about this a lot is you might say, what is going on there? And you get a new model, or you get a better understanding. For example, the precession of Mercury, scientists were looking and they said, what is going on there? And they thought, maybe there's another planet there. This was the hypothetical planet Vulcan that they thought could be explaining this. And then Einstein came along and said, oh no, general relativity, which was like a huge revolution and is so important in astronomy. And yet I still use Newtonian gravity for basically all of my research. And so like, there's levels here. And just because, there's a new shiny thing that's maybe more accurate doesn't mean that the old thing is not useful anymore.
So true. So true. Well, we're gonna move on to virtual stargazing here in a minute, but before we do that, I wanted to mention that the viewers may have noticed that we're all wearing hats today, and of course you know that it's National Hat Day. No, not really. It just so happens that I am shamelessly promoting the fundraiser that Wyoming Stargazing is in right now, Old Bill's Fun Run. We get a match on all donations for this month up through the 17th. And so if you like what you see on the Cosmos Show and you want to support all the other cool work that Wyoming Stargazing does, you can go to our website, wyomingstargazing.org, and there's a nice like floating banner across the top that shows you how to donate through Old Bill's Fun Run to help us get a match on all of our donations this month. So there unfortunately isn't a run this year because of COVID. There's usually like a big like event and the whole town comes out and there's a 5K race and all the nonprofits are out there with their booths, and we've brought out our solar telescopes every year to show people sunspots and solar prominences, but because of COVID, that all got canceled. So there's going to be a film crew going around town filming individual nonprofits kind of doing their thing at their offices. So we're going to get filmed tomorrow, just having our solar telescopes out in front of our office, and maybe some folks will wander by and we'll show them some sunspots and that kind of stuff. And it's also going to be a pizza party for our staff, so it should be a lot of fun. So if any of y'all are in town tomorrow, feel free to stop by the Wyoming Stargazing office and get some pizza and look at the sun. So I just happen to be wearing this hat to shamelessly plug the fundraiser, and then everybody else thought it would be a cool idea to put a hat on as well. So they can all tell you a little bit about their hats at some point later on. But we're running late as usual, so we're gonna roll into virtual stargazing right now. We connected with our local virtual stargazer, Dr. Mike Adler, a week ago or so, and he showed us some cool clips of stuff that he imaged with his telescope. So we'll show you some of the clips from that virtual stargazing program, and then we'll be back with our special guest, Natalia Guerrero. So stick around. We'll be back soon.
Hello, folks. My name is Mike Adler. I'm Vice President of Wyoming Stargazing. I also had a professional career in working for General Electric for 30 years. I got a PhD from MIT in solid state physics in 1971, and now I'm indulging some of my hobbies, one of which is astrophotography. So tonight we're going to use my observatory and my telescopes that are located here in Jackson, Wyoming, and we're going to look at 3 deep space objects. The first thing I'm going to do is show you my observatory, and there's a brief introduction to the telescopes. So this is the observatory. It's one I built here in 2014. It houses 3 telescopes, a 6-inch refractor, a 20-inch cardiotropic, and then a smaller one, 12.5-inch. Cardiotropic means it's using a series of mirrors to do the imaging rather than through a lens. And these 2 telescopes have cameras on them, and we're going to be using those to take brief, short exposures of these nice objects. So I'm going to move on to the screen that controls the telescope. So this is a program called SkyX. It's now tracking the night sky. It has a motor system in it that moves along with the rotation of the Earth. So when you look at something, it doesn't move away from you. It sits there and you can look at it for hours if you wish, which I do when I'm taking my special photographs. The first object we're going to look at is almost directly overhead at the moment. It's called Messier 57, but more popularly known as the Ring Nebula. It is a planetary nebula. I already have the telescope actually pointing at it just to save a little time. So now we're going to move to the program that I use to control the camera on the telescope. And in fact, I just took this picture. It's about a 15-second picture of the Ring Nebula. And it has a ring shape, so thus its name. So this nebula is what's called a planetary nebula, which is it's a remnant of a sun-like star that has essentially run out of its fuel. And once it runs out of its fuel, first burns hydrogen, converts the hydrogen into helium, then that reaction, when the hydrogen is all gone, it starts burning helium. When the helium is all gone, it tries to burn what's left, which is carbon, but it won't get hot enough to do that, and thus the star essentially stops. Its nuclear reaction stops being a star, and the matter in the star just sort of effervesces away into various interesting shapes, like this one, a ring. And the little white spot in the center there is the leftover star, which is a white dwarf, a very dense star at the extreme level of density that electrons are allowed to be. Anyway, this Ring Nebula is quite interesting. It's called a planetary, but it has nothing to do with planets. It's just they call it a planetary because of its round. It's 1 light year across in actual size, so it's huge. The nearest star to us is 4 light years away, other than the sun. So you can see this thing is huge in size, much, much bigger than our solar system. It's about 2,000 light years away. So we're going to now go back to the screen that controls the telescope, and new share. And we're going to move the telescope to a different spot. So I'm going to now move it to a spot in that corresponds to the location of something called Messier 17. And I'm going to hit find here, and there's Messier 17. It is this bright band through here. You can't, this gray area is clouding it, but is the Milky Way, the summer Milky Way. And so this is located right in the middle of the summer Milky Way. So I've told it to find it. There it is. Now I'm going to tell it, the telescope, to move to that object. And it says, yes, I'll do that. And now it's moving there. And when it gets there, it's going to stop. It's there now. And now it's tracking at sidereal rate, which means it's tracking the Earth's movement as we spin. Okay, so we're going to go back to the screen that controls the cameras and look at a different object that the telescope is now pointing to. And while I was talking, I actually did the exposure already, and this is it. So this is a very interesting object. There's a lot of really beautiful nebulas in the summer Milky Way, and M17, or it's also known as the Omega Nebula or the Swan Nebula. To me, it looks more like a fish. As you can see, sort of a fish head and a tail here, and you can almost see scales running on it. But anyway, that's not what it's called. But it is a nebula. What is a nebula? A nebula is a cloud of gas and dust. And in this case, the stars in this nebula are causing what is this gas. In this particular nebula, the gas is largely hydrogen and oxygen with some sulfur. And the stars are causing these elements to be excited to a higher energy state. They give off light, and they return to their lower energy, their ground state, by giving off light, and that's the light we're seeing. So this is called an emission nebula, and it's a very beautiful object, and it's right near several objects we looked at in past virtual stargazing sessions, such as the Eagle Nebula and the Trifid Nebula. But anyway, this one's quite beautiful, and we can do it in color, but right now we're for this type of virtual stargazing, we're doing everything in black and white. The camera is a black and white camera. Okay, so now we're going to move on to the third object for the night. So I'm going to change the, we're going to go to a new share. I'm going to share my telescope screen again. And so here we are pointing at M17, and I'm going to now tell it to go to a different object, which has a different designation. It's NGC, standing for New General Catalog 6960, and ask it to find it. And it's actually up here towards the, a little bit towards the north and west of where we're pointing right now. So now I'm going to tell the telescope to go there, and here it is, and it's going to shoot right up there quickly. Now, this is a very different type of object. We're looking at all the objects tonight are looking at our nebulas, and the first one was a planetary nebula, which is a leftover remnant of a sun-like star. We looked at a gaseous nebula, M17, which is actually, I should say, all nebulas are, all stars are formed in these clouds of gas and dust. And what happens is some event causes the gas and dust to start collapsing. And if gravity then takes over, and if the temperature of the cloud gets up to 17 million degrees Kelvin, nuclear reaction star and a star is born. Well, this is another cloud of gas and dust, but this one is also a leftover remnant of a star, but it's not a leftover remnant of a sun-like star. This is a leftover remnant of a star that's maybe 10 times the size of the sun. And when a star that large runs through its fuel, it doesn't end quietly. It compresses, in this case, iron. It's made elements all the way out to iron. And when it tries to compress the iron to start a new nuclear reaction, it can't, because iron has the nucleus has the highest energy of any nucleus, and it takes more energy, not less energy, to start another nuclear reaction. And so the star compresses and compresses and compresses and then explodes. So what we're going to now do is go back and take a look at this object. Go back to the camera program. And while I'm talking here, I'm going to taking a a picture, which is about 30, in this case, a little longer, 30 seconds. And let's see, there's that picture right here. And here it is. And so this is a picture of this nebula, which is called the Veil Nebula. It's located, I should say, in the constellation Cygnus, which is the swan, or in some cases it's referred to as the Northern Cross, because it has the shape of a cross, and it's also very high in the sky at the moment. And so this has a shape. This is called the witch's broom. I think of it more as a woman flying in the sky with a flowing dress behind her. But it is a remnant of a star that went supernova maybe 10 to 20,000 years ago. It's about, the total size of the nebula is about 6 degrees in the sky, which is about 6 moon diameters. But this object here is about the diameter of a single moon. I'm only looking at part of the Veil Nebula in this one particular place. This is the brightest section of it, so it works well for short exposures like we're doing here. This was discovered by William Herschel in 1784, and he didn't know quite what he was looking at, but we do now, and this is a beautiful cloud. I'm going to show you, it's about 1,400 light years away. I'm going to show you what this object looks like when you do a long exposure of about something in excess of 30 hours. And so then we're going to end the talk, end this session on that note. So we'll go to a new share and share this. And so here it is. And as you can see, it has this, that's that bright star we were looking at, and the arms were sticking out. The flowing, the angle here is a little different. I needed to do this to get this picture done, but as you can see, this is a fantastically beautiful object. It is done with what's called narrowband filters. So this is a false color image, even though the colors are fairly close to their true. The greenish color here is coming from oxygen. That is, again, I mentioned that a lot of these nebulas are, in this case, are emission nebulas that are emitting light from gases of oxygen, hydrogen, in this case, just oxygen and hydrogen. So the green-blue color is coming from oxygen, and the reddish color is coming from hydrogen. And in this, when you see the full picture in detail like this, you can see what I meant about a woman flying through the sky with a, in this case, a red-headed woman with a beautiful flowing dress. And so I think it's one of the most beautiful objects in our current night sky. So that's the end. I'm going to say goodbye for this session.
Welcome back, everybody. We're here with our special guest, Natalia Guerrero, consultant with TESS. Natalia, thanks so much for joining us tonight.
Glad to be here. Thank you for inviting me.
Yeah, of course. Well, before you get into telling us a little bit about the work that you're doing, I'd love for you to answer the question that we have all of our special guests answer when we first start, which is, what's the one thing that nobody asks you that you wish you would get asked?
I would love to be asked more about how do we think about exoplanet exploration, because that's always the question I do get asked is, okay, when can we go to the next exoplanet? I'd like to be asked also, like, how do we take into account social science, history, all of our understanding of conflict and history on the globe, and wrap that into our science? Because we as astronomers are not experts in those fields by any means, but that knowledge is here on Earth. And so I think I would love to hear that question more, is how do we think about those things more in our research on exoplanets?
Yeah, that's super cool. That's kind of like the should we go question.
Yes.
Nice. Yeah, a big topic of discussion there.
Definitely.
You told me a little while ago that you actually just started grad school, so congrats on doing that.
Thanks.
Yeah, but how long have you been working on the TESS mission?
I have been working for TESS since 2016. And I started as a lab technician for the 4 TESS cameras that were built at MIT's Lincoln Lab and then tested at MIT in Cambridge, Massachusetts. So I did that for 1.5 years, and it was such an amazing experience to go into the lab every day and know that the thing just on the other side of the clean room wall was going to go to space. That was just unbelievable, so exciting. So that's the first picture on the left that you can see is me standing in front of TESS loaded onto its Falcon 9 rocket. That was in April of 2018 was when TESS launched.
Very cool.
Yes.
And you brought some other pictures to show us, right?
I did. So this is if we can go back to the previous slide. So yeah, so TESS launched in 2018 and it has been orbiting the Earth ever since. And it is looking for exoplanets, so planets around other stars. And so in my work with TESS, since its launch, I've been studying exoplanets and managing our ever-growing catalog of exoplanet candidates. So these are planet candidates that I'll talk about this a little bit later, but that we see in the TESS data that we think, okay, this could be an exoplanet. And then we rely on a network of observers all over the world and using telescopes in space as well to confirm these as bona fide real exoplanets. And so I helped to design the process, and I have helped manage the team from 2018 onwards that has created this catalog of TESS objects of interest. And we now have over 4,000 candidates in this catalog. And so that's a lot since the start of the TESS mission, and it's continuing to grow every day. And then on top of that, I am also an artist. I am really interested in using art as a tool for better understanding my own work as an astronomer, and using the spontaneity and the serendipity of art as a tool for discovery and a means for deeper understanding. And so those 2 pictures on the right are myself working with the director of the Lorelei Ensemble, which is a vocal ensemble. I collaborated with them and with Elena Rohr, who is a composer at MIT, to put together a concert of music inspired by the first year of TESS's discoveries. And that was premiered at the first TESS Science Conference in 2019. So I was really interested there in using the arts to help us as astronomers at this conference make connections that maybe we wouldn't have made just listening to talks and visiting with each other.
That is super cool.
Thanks. I'm really excited to do more of that as part of my graduate work as well.
Awesome. Well, I hope you get to do that.
Thanks. So yeah, I'd love to tell you a little bit more about TESS and what it's doing. We can see it's very shiny in this poster that was just made this summer by the NASA Exoplanets Exploration Group. So let's go ahead to the next slide and roll the video. There we go. So TESS has 4 cameras I mentioned before, and I helped test their performance of how they would do in space. And each of these cameras has a really wide field of view. It showed 24 by 24 degrees per camera, which is about the size of Orion. If you go out later and see Orion, that's 1 TESS camera. And so 4 fields of view for a given TESS camera, we stack them on top of each other and make what we call a sector. And so TESS stares at 1 sector at a time for 2 orbits for about 27 days total. And then it steps to the next part of the sky and has done that since 2018. So it first covered the southern hemisphere of the sky, then flipped over, covered the north. We just finished this summer looking at the southern hemisphere again. And now we're going to turn back to the north. And on top of that, TESS is going to rotate and look at the gap in the sky that it wasn't able to look at. And that's going to include fields from the K2 mission. And so there's a lot of exoplanets in there that people are really excited to see again with TESS. So that's going to be really exciting. So I wanted to talk about TESS, but also what it does and why that's important. So if we can go to the next slide.
It was for Kepler, right?
Yes. So Kepler's follow-on mission after its reaction wheels broke down was K2. Thanks for catching that. So I mentioned that TESS has these wide field cameras, and this, I think, gives you a good idea of just how wide those fields are. You can see that each sector fills in a little bit more of the sky. And so in its first 2 years of observing, TESS filled in almost 70% of the night sky. And we hope by the end of its 4th year of observing, we'll have almost 88% of the sky covered. And you can see the galactic plane swooping through there. And I think this is a really beautiful way to encapsulate all of the amazing work TESS has done. So this gives you an idea visually of how TESS is this wide field survey telescope. That's the S in TESS, the survey satellite. So if we go to the next slide, one of the big surprises with TESS is that you're staring at this part of the sky for 2 orbits and 27 days at a time. And so the north and south, you get a year of observations. And so this is millions of stars that you're observing. And so there is so much interest in all of these stars, what they're doing. And so this is an animation created by scientists at the Leibniz Institute for Astrophysics in Potsdam for a project between them and the University of Hawaii to use the TESS data, which is taking a full frame image every 30 minutes for a month. And then for select stars, like smaller images just of that star every 2 minutes, to essentially put together what I think of as like a stop motion movie of each of those stars. And using this to better understand the astroseismology or the interior behavior of the star. So its pulsations over a series of minutes or hours. And we have struggled to have this fine-grained data set for stars for many years. TESS is like the first of its kind to have this volume of stars. And you can see all of these stars. What this is showing here is we also have Gaia data. Gaia is another space telescope that's given us really accurate information on the distance to each star. So with TESS giving you how close these stars are to us and Gaia giving distance, people are able to make a lot more connections about the abundance of stars, what happens to different kinds of stars as they evolve. Do older stars behave a different way than younger stars? Do they act differently in the galactic plane? So TESS data is this amazing starting point for stellar astrophysics. Even though it started out as an exoplanet mission, it's now serving for people who also want to study stars. I'm curious, there's another application of TESS data that I would have never expected, but that it has been also used for since it launched. Can any of you guess what other astrophysical object we might be able to detect with TESS? Nora, I think you probably peeked at my slides.
I think Nora's got it.
I did not peek at your slides actually, but I mean, I am in this field, and so it's probably a little bit cheating because I've heard talks about it and stuff.
What is your hunch?
I think you're talking about Planet 9, right?
That's another one. That's not the one I'm going to talk about, but yes, people have been searching for the invisible Planet 9 using TESS data because you can get information about asteroid tracks and tracks of solar system objects from these stop motion movies of the night sky with TESS. There's another one though.
Are we just going through the transient list? So exoplanets, stars, solar system objects, supernova?
Close. Let's go to the next slide and talk about it. This is, TESS was able to detect a tidal disruption event. So what is very likely a star, which has unfortunately been caught in the tug of an active black hole at the center of a galaxy. And what happens is as that star whips around, some of its outer material is yanked off by the black hole. And when it hits the material of the black hole's accretion disk, there's this big flash of light. And because it's in this predictable orbit, you're able to know when the next flash is going to happen. It's kind of like an old faithful is what they were calling it. And so this had been studied using X-rays, using high energy gamma rays, using a whole set of other wavelengths, other types of light. But TESS was able to provide optical information about this particular transient event and ascended into the ranks of multi-messenger astronomy or multi-wavelength astronomy. And so I think this is a really cool example of TESS, again, seeing this bright flash of light in the sky and being able to connect that to other telescopes. And I mentioned Gaia before, but it's this really collaborative, like, group project forward telescope that I really love. But yeah, I forgot about Planet 9. That's like the sleeper hit of TESS is solar system objects.
Well, it's another way to be like, oh, we didn't find it, but it might still be there. Can't disprove it.
I'm kind of curious, so how everybody feels about Planet 9. I mean, you can just do a quick little vote. Who thinks Planet 9 is an actual planet out there, or whether it's just a mathematical anomaly that we just don't understand yet?
I just don't think we have enough data, really. I mean, so the main evidence for Planet 9, right, is this clustering of the orbits of trans-Neptunian objects. And there was actually a paper that just came out maybe 2 weeks ago on Archive that was re-examining this basically significance of this clustering effect, because this being science, someone else had published a paper saying, no, this isn't actually significant. It's because of biases in the surveys. And they're still claiming it is, and it may well be, but there's 11 objects that they're using for this. And it's coming from surveys that have really big gaps in their visibility of the solar system. So I just think we need more data, to be honest. I'm not totally convinced without seeing more data.
It is a little tenuous a case, but I guess on the planetary formation side, right? Weren't sure about hot Jupiters. Would we miss this one? Like, is there any reason there can't be planets out there?
It actually is pretty difficult to get planets out there.
You think it is?
Well, we think it is. So it probably couldn't really form there because the disk is just not going to be dense enough to like form planets hundreds of AU out from the star. There are dynamical processes that can get planets out there, but they're of somewhat limited effectiveness. I actually, my very first paper I ever did was about wide orbit planets, and yeah, it can be difficult to do.
Funny side on the detection side, but actually our field is going after it too, because we're microwave telescopes and it would be really dark optically, but it'd be pretty bright microwave. We just don't do a lot of transient searches. So it's like trying to figure out if we can do analysis techniques to go chase after it.
That'd be great.
So I'm all for it because that would be a cool detection for our telescopes.
No, I mean, I think it'd be really cool if it existed. I'm not like anti-Planet 9. I'm a little bit skeptical at this point.
I don't know, Nora. Sounds like you don't want it.
I mean, because like people have been searching like pretty heavily for it, and it's not come up yet.
All right. So when Nick's team gets the initial detection and Natalia's team confirms it, then they'll have the final word.
I will be the first in line to congratulate them.
All right, Natalia, we'll go back to you now.
Sure. Yeah, let's go to the next slide and talk about exoplanets, which so the way that TESS looks for exoplanets around other stars is there's other types of telescopes that can actually like take pictures of the exoplanet using sneaky optics is what I call it in my head, but using image reconstruction essentially. But those planets have to be super far away from the host star because the host star is much, much brighter, thousands of times brighter than the planet. And so what we actually see is if you start the animation, as the planet orbits its host star, oh, I guess it didn't import as a video, that's okay. As the planet orbits its host star, it blocks out a tiny amount of that star's light, usually on the order of 1% or less. And when that happens, you see if this is the amount of light coming from the star, you see a little tiny dip from where the planet crosses in front. And so a bigger planet will make a bigger dip, a smaller planet will make a smaller dip. And this transit and what it causes in the light curve is the signature that we're looking for. And so when we're looking for this with computers, we train it to something that looks like a box or a trapezoid and teach and say to an algorithm, okay, let's search for this shape in this light curve. And as we've gotten more computing power, more machine learning tools, we can train a computer to recognize transits the same way humans have over the last several decades started to get really good at identifying transits and light curves, and use machine learning to do this as well. So that is the transit method, and that's the method that TESS uses. So if we go on, so I'll walk you through a little bit of how the transit method works. So you take a star, so this is a given star in the TESS data, and you draw a box around the pixels where you want to count up the light. And then next slide, you basically plot that light as it changes over time. And this light curve you can see has a very nice periodic dip in time, about every 4 days. And if you were to assign a pitch to the baseline amount of light, and then listen to the pitch drop basically every time the amount of light drops, it would have a very distinctive sound. And I've gone ahead and used the Astronify Python code to make this sonification, and I think we'll be able to have folks listen to that in the chat. So that is this particular exoplanet candidate. So what do folks think? Is this an exoplanet based on this crash course that I just gave you? Show of hands.
I'm going to say no.
All right, we got to know, we got to shrug.
I can't speak with any authority on this subject. I'm a physician.
Does it look healthy?
I take care of the retinal burn from staring at the sun too long. That's what that is.
I'm trying to think into it too much, right? It's supposed to have the double dip from when it goes behind as well, right?
Right. So that's like, if you see that often, it will be much, much smaller than the primary transit. So you can see it for some exoplanets, but in this case, it is not visible. It's the majority of the time it's not visible. All right, so I will put you out of your misery. This is an exoplanet. If we go to the next slide, this is actually Kepler 12b. So this was found by the Kepler mission. And you can see that it has this very nice periodic transit pattern. They happen sort of equally in time, which indicates that it's a planet in a circular orbit, most likely. And you can see there's kind of like a downward slope. And that is actually from an issue with the Kepler instrument where you had the spacecraft slowly moving away from the star. So your baseline amount of light goes down. All right, let's try another one. So is this an exoplanet? We have our box around our star. We have our light curve. We have a sound clip if you want to hear what this light curve sounds like. Have a head shake from Nora. What do folks
Based
think?
on the last one, you got to say no, right? This one doesn't look nearly as clean.
Yeah, it looks pretty distinctly different. And it doesn't
Yeah,
look
no,
like the period is really regular. What was that?
I'm wondering if it's like multiple exosolar planets as opposed to just one.
That light curve needs to be detrended before you can say anything.
So the skeptics have it. If we go to the next slide, this is actually, yes, stellar variability. What Nora's talking about is taking the star signature out of the fitting for that periodic change in brightness that's very slow. This is happening over a course of several days where it's slowly getting brighter and then stepping down in brightness in this repeated pattern. You would take that out using an algorithm and then look again and try to see any transits there. So one more. Is this an exoplanet?
Eclipsing binary.
Regular. Oh, what was that, Nora? Sorry.
I'm voting eclipsing binary
And why is that?
because it looks like it has secondary eclipses.
Mm.
But it's kind of hard to tell. Keep in mind, I'm looking at it very tiny.
Yeah, I mean,
Admittedly,
there's like
I also like didn't detrend these before making these just so we could get more of the like interesting sound in there.
Yeah, it looks like a really big dip. So it'd have to be like a pretty substantial exoplanet, right?
There you go, all in on the hot Jupiter.
All right, so if we go to the next slide, this is an exoplanet. In fact, it is a hot Jupiter. You are right. Very nice.
Trophy to Nick.
This is a hot Jupiter. And if we go one more slide, this is TOI 432b. Oh no, I didn't include the picture. We had an artist's illustration of what this planet would look like. It's much larger than planet Earth.
Just imagine Jupiter, but hotter.
Yes, much closer to its host star. So that one had a period also, I think, around 4-ish days. So that is in a nutshell. Oh yeah, so, and Danielle, a hot Jupiter is, Nora also mentioned this, of it's highly, we have Jupiter, but it's 5 times the distance away from the sun that Earth is. But the first exoplanet that was discovered in 1995 was days, its orbit was days around its host star. And we don't have an example of that in Earth's, in our solar system. And so this hot Jupiter, termed so because it's right next to its star, is a common type of exoplanet, but we're not sure why yet, ... So that type of visually inspecting exoplanets, that's like a little tiny peek into what we do as a team to create this TOI catalog. We take the best of the best, spit out from the algorithms and from machine learning, look at those visually, label them, consult with team members to make sure that we all agree, and then put those into our catalog. And when you do that, you can start to look in ensemble at these thousands of exoplanet candidates we have. And one common way we like to look at them is looking at the orbit length, so how long it takes the planet to orbit its host star, and also the planet's size. So I have a couple of different sized orbits there to help you imagine what this would look like. And then on the next slide, I've added in planet size. So this is going from about the size of Earth to 4 times the size of Earth, 10 times the size of Earth. And I've picked those numbers because Neptune is 4 times the size of Earth and Jupiter is 10 times the size of Earth. So if we start adding TESS TOIs, TESS objects of interest, to this graph, and we start from 2018 and roll the clock forward, that is what we're going to see on this next slide. So we have our axes, and I've drawn lines where those different sizes are. And so it's very easy to find hot Jupiters because their periods are so short. And so that's that big blob right at the top. And you see as time goes on, as the years roll on, TESS started finding more and more and more exoplanets. And this is really exciting to see because we're finding those hot Jupiters that are very easy for transit telescopes to find, but we're also finding smaller planets. You see around between the line for Neptunes and Earths, you're starting to get a lot more dots in there. And these are at periods that are around 10 days, which are short and easy to find for something like TESS. But we're also getting longer period planets, so things around 100 days, which is really exciting. Mercury's orbit is around 88 days for reference, to like frame that in your mind. And so there's all of these interesting patterns. And I look at this graph and what I see is a giant to-do list, because each of these dots is a potential exoplanet, and it has its own story, its own journey. It needs to be observed, it needs to be studied. And depending on what happens, if these get crossed out as not exoplanets, or if they get checked off as real exoplanets, we're going to be able to draw connections and start to make patterns about why are there so many of this kind? Why did we detect so many of this kind? Does that mean they're common, or does that just mean they're easy to find? Like, what about these rarer types? And so if any of you like collected Pokemon or trading cards of any kind, like I think exoplanets is like the next level of Pokemon. You got to catch them all.
I had a quick question on this, which is, so transiting always kind of astounds me because of it's almost serendipitous how hard it seems to be to have the observation aligned on the planetary axis, right? If you're looking at the system face on, you don't see a transit. You got to be right on like the knife edge of the system to see it. And so, that means like TESS is playing a statistics game with observing millions of stars to see some small fraction that the alignment's actually there. I was wondering, what is that fraction? Like, at this point, you're showing us thousands of it. Is that a % of the stars you're looking at, or kind of how unlikely is it to be aligned just so?
That's totally a question that we think about all the time, is like, what is the underlying occurrence rate? And Kepler helped answer that question because they stared at just one patch of the sky and tried to count up all of the transiting exoplanets they could possibly find in that patch of sky and create like a statistical sample, a census basically, that you could then back out from there. How many should there be statistically? I don't know too much about that. And then like my first approach at this would be also like the geometric approach of, you're right, we have to be very lucky with how the orbit aligns with our line of sight. And so it would probably like taking in the full like 180-degree range. Like we can only see a few degrees of that range.
And it gets worse as the planets get farther away from the star. So you
Right.
see even less of them, right? Because if they're close to the star, they can kind of move around a bit and still transit. But if they're far away, you really got to get lucky.
Yes.
But I think what I would take away from, we've discovered so many transiting exoplanets, even though it's very rare. And I think the quantification studies have shown, but just what I would say as a takeaway is basically all stars have planets. They are ubiquitous.
Yep. And that's like a huge takeaway that like when I was learning about space in elementary school, like was not a fact in the textbooks. That has been a discovery like of this millennium. And to me, that is wild that this field is evolving as like we are moving through the academic path.
Right, yeah, just this pod is new things since 2018, which is not that long ago.
Nope.
Yeah, I mean, I think I read somewhere recently that the emerging consensus is that there are probably more planets in the universe than stars.
Yes, because if you have there, I think that was the second big takeaway from Kepler. The first was planets are common, and to every star there is likely a planet. But I think there was a second takeaway that like multiple planet systems are more common than single planet systems. And so yeah, that would totally be a huge like factoid to take away from the last decade or so of exoplanet exploration. So yeah, I just have one more thing to say, and that is that TESS is providing this data that can be used both by professional astronomers who are interested in exoplanets, and we've also talked about all of these different other kinds of exoplanet astronomy or non-exoplanet astronomy, but the TESS data are public, and there's several citizen science projects and community science projects that are focused on having people all over the world participate in real exoplanet research. So I've put a couple of those on this next slide. So if you are interested in exoplanets and want to learn more about them, you can definitely get involved. The Planet Hunters project on Zooniverse often uploads the latest sector of TESS data, and you can label transits. So if you found guessing, is this a planet fun? Like this will be right up your alley. If you have a telescope of your own and are passionate about following up exoplanets, there is also this new project that has come online recently where you can participate in re-observing known exoplanets and helping make those measurements of when they transit, how deep their transit is, more precise. So that's a really exciting project as well. And if you just want to learn more about exoplanets, we just finished our second TESS Science Conference that was in early August, and all of the talks from that are on YouTube, including, this is my self-plug, my talk on more in depth, the TESS Objects of Interest catalog. So if you want to learn more about that, those are all on YouTube as well. And this also covers all of the other types of science, including Planet 9 science, that TESS is contributing to. That was like one of the huge surprises for me at this conference was exoplanet talks only took up like a day and a half of a 5-day conference, and everything else was non-exoplanets related. So I thought that was really exciting. So if you want to learn more about what TESS is doing, definitely check that out.
Well, I am definitely going to check that out. That is super cool stuff. I actually have a question for you, Natalia. So I correct me if I'm wrong, but I think like the first several exosolar planets that were discovered were actually discovered using the Doppler method, as opposed to what TESS uses and what Kepler used, which is that called the photometric method or something like that?
Right. So they use the spectrum of the star, whereas TESS just uses straight up the optical light from the star, counting up the light in all the pixels.
Right. And so my question then is, so why is that, at least from what I'm aware of, like become the dominant way of finding exoplanets? Why aren't we using the Doppler method that was used back in the day in the 90s?
Only 90s astronomers will know. The radial velocity method is continued to be used because you can set up a spectrograph on a ground-based telescope and get a lot of what you're looking for. Is as the planet goes around its star, it's going to be tugging on its star. And so that is going to be red and blue shifting the spectrum of the star throughout the planet's orbit. And so you brought up earlier, for transits, you have to be pretty lucky with the alignment. With radial velocity, that's not the case. They can be at a larger range of orientations with respect to each other. But yes, so radial velocity was super easy to do, easier to do from the ground. But the CCDs weren't there yet for transits. And so CORO, I think, was one of the very early space telescopes for this. We had to wait for CCD technology to be able to get that level of precision for transits. I mentioned before, like less than 1% of the light will be blocked. So like 100 to 1,000 parts per million is what we're talking. And that's not a lot of light. So you have to have detectors that are really precise in what they're able to measure and count up those numbers of photons. And so the TESS detectors, for example, and the Kepler detectors, the technology had come along far enough by the early 2000s that we said, we're ready, we can put these in space. And also on the ground, you can measure, there's the KELT, HARPS, there's a number of transit photometry telescopes on the ground now.
Cool, thanks for explaining that, I appreciate it.
I think I would add that with transit photometry, it's easier to do a large number survey like Kepler and TESS, where you can really get these big numbers, whereas RV is really good at like single systems, and it takes, like, you have to get a spectrum, which is like a little bit harder to do, and so it's a little bit more detailed for like a single system. But they're very complementary methods, because the transit method will give you, say, the radius of a planet, but it won't give you the mass, but the RV can give you the mass but not the radius. So like combining them is like the goal. Yeah. So I think RV is used a lot for follow-up of transit.
Definitely.
Very cool stuff. Natalia, thanks so much. That was awesome.
Thank you for inviting me. This was really great. I had an awesome time.
Yeah, well, thanks so much for being here. Well, we're over time as normal on the Cosmos Show. Good problems to have, I suppose. But thanks to our special guest for being here, and to our co-stars, for all the folks behind the scenes who make the Cosmos Show possible, our streaming master and graphic designer, everybody on the board of directors of Wyoming Stargazing, and all of our donors who support the programs and all the other stuff that Wyoming Stargazing does. Don't forget about Old Bill's Fun Run. And special thanks to all of you who watch these shows on YouTube and when we stream them live. We really appreciate you all tuning in, and we hope to see you next time. But until then, be well, and don't forget to look up. We'll see you in a couple weeks. Bye.